Somebody hit that light for me, one of the lights back at the back. All right, so we're going to move on to chapter 3. All right, this is chapter 3. So next week, we're going to take a midterm exam on Wednesday, okay, on chapters 1 and 2. All right, but we're going to keep it moving, and we're going to start chapter 3. All right, so chapter 3, the first part of chapter 3 deals with vectors, all right, or kinematics in 2 dimensions. So so in the previous chapter we dealt with kinematics in 1 dimension, right? That was the previous chapter. That's chapter 2, kinematics in 1 dimension. Now we're going to talk about kinematics in 2 dimensions. So motion. Hello. Yes, sir. Yeah, I was just calling to verify all of the information. I talked with Ms. Franklin. Yeah. Okay, is that the side? That's on the side opposite the police station. Yeah. Okay, 6:45. All right, I'll be there. We'll be there. Me and my 3 students. All right, thank you. Yep. So yeah. So we're talking about motion in 2 dimensions. So as you see here, the guy is skiing or something, right? And he's going down a hill, right? So not only is gravity pulling on him, right? But because he's going down an incline. So when you go down an incline, right, you're not going in 1 dimension. 1 dimension is free fall. That's what we've been talking about, right? Right? Yeah. Okay. 1 dimension is free fall. But if I'm going down an incline, that's 2 dimensions. Because I have motion in this direction and in this direction at the same time. Correct? So the contents of chapter 3 are as follows, right? We're going to make a distinction between a vector and a scalar. We're going to do some go over some graphical methods in adding vectors. And we're going to do some subtraction of vectors, multiplication of vectors, a lot of vector math, right? And then we're going to do vector components. And in adding vector components, we're going to have to harken back to our trigonometry, right? Sine, cosine, theta, all of that stuff, right? And so then we move into projectile motion. So we're going to take what we learned in chapter 2 with 1-dimensional motion, and we're going to apply our vectors to the motion first, and then we're going to look at both dimensions affecting the object at the same time. So a projectile motion, right? Not 1-dimensional motion, not straight down or straight across, but like this, right? Like that. A projectile, like a missile. Okay? And solving projectile motion problems, All right, we're gonna get quite a bit of practice with that. All right. So, what is a vector and what is a scalar? Right. So, a vector has a magnitude as well as a direction. Right. So, a vector. So, if I ask for directions to travel somewhere, right, and you just tell me how far. For instance, if I say, hey, how do I get to New Orleans from here? From Baton Rouge. How do I get to New Orleans? And you tell me, oh, you just get on I-10 and go 100 miles. Is that enough information? What's missing? The direction, right? Without the direction, it makes no sense. So there's a lot of different values in science where if you don't specify what the direction is, then it's useless. Okay? You have to say what direction. That is what we call a vector. Okay? And some examples of vectors are displacement, right? Displacement is like what? Where you start from and where you end. Right? Velocity. Right? That's different from speed, remember? Because it doesn't involve distance, it involves displacement. All right? Force. Right? Force is another vector. Right? We have to identify in which direction a force acts on an object. Right? For instance, with gravity. The difference between me throwing the ball up and the ball what? Coming back down. When I throw the ball up, what force is acting on it? Gravity. And what is it doing to it? It's acting against the ball. When it's coming back down, what force is acting on it? Gravity again. Only in this instance, it's what? Acting in the same direction. That's why it speeds up when it comes down and slows down when it goes up. Okay? So a scalar is just a number or something that if we don't say what direction it's in, it's fine, right? It still gives us a lot of information. Like, well, in the case of time, we know that time only moves in one direction, right? So, but some other ones are what? Temperature and mass, right? And mass is what we call an intrinsic property of an object, right? Meaning that it fundamentally does not change, right? Unless you change the atomic structure of the object. And you change the atomic structure by melting, evaporating, all of those different things, okay? But mass is something that does not change, okay, for the most part. All right, so let's talk about displacement. Well, let's talk about addition of vectors using the graphical method, right? So, so the graphical method, right, is what we call the tail to tip method, okay? And we're going to discuss that in the next couple of slides. But the name is exactly what it says it is. The tail to tip method. That means I take the tail of the second vector and I attach it to the tip of the first vector. That's called tail to tip method. Okay? Now that's not a very accurate method, okay? Or it's not the most accurate method that we're going to use, but it's pretty reliable, okay? It's pretty reliable. All right, but as you can see here, we have two vectors, right? First vector has a magnitude of what? Come on, I need to hear somebody. Y'all gotta speak up. Huh? What is the magnitude of the first vector? 8 kilometers. The magnitude It's 8 kilometers in what direction? East. So I need 2 pieces of information. I need how big is the vector and in which direction it's pointing. If I don't have both of those 2 pieces of information, I'm not going to be able to move forward. So I have the first vector of 8 going east, and then I have a second vector of 6, magnitude of 6, okay? Please, well, I'm not gonna say that, okay? Because I know it's gonna happen anyway, so I'm not gonna set myself up like that. Because I know somebody's gonna ask me, maybe 2 weeks from now, what is magnitude? What does that mean? I'm telling you what it means right now. It's the number, magnitude of 8. Okay? So hopefully nobody in here is gonna ask me that question in the future. Magnitude of 8, direction east. Okay? So you have 2 vectors going in the same direction, right? Then obviously I can do what? Add their magnitudes and I get 14, right? But in the case where what? I have the first vector going east, and then the second vector going what? West. Okay? So when I add these 2 vectors, I get a displacement of 2. Okay? All right, so, like I said, every motion, if the motion is in 2 dimensions, right, then this is what we have, right? And we remember this from trigonometry, right? Trigonometry, hypotenuse, right? Pythagorean theorem, I'm sorry. Pythagorean theorem, right? D1 plus D2, right? This is actually the tail to tip method, actually what they're showing here, but eventually it leads to the Pythagorean theorem, and we'll get to that, okay? But this is the tail to tip method. I take the tail of my second vector and I attach it to the tip of my first vector. I take the tail of my first vector and attach it to the tip of my second vector. And now it's completed, right? I have a 3-sided polygon, otherwise known as a triangle. But there are cases where we will have more than just 2 vectors. In that case, then we'll have another side here, right? So if I added another vector, D3 pointed, if D3 was like pointing right here, right? Then this is just gonna move up to D3. But it's gonna be a 4-sided polygon then, because I added 3 vectors, right? So if I have 2 vectors, if I'm adding 2 vectors, I should end up with a 3-sided polygon, triangle. If I'm adding 3 vectors, I should end up with a 4-sided polygon. And we're gonna get some practice with that. All right? So this is just showing you also tail to tip. This is also the tail to tip, right? Only in this instance, I added the second vector. Somebody? What was the difference, huh? What's the difference between this one and the last one I just showed?
He started going north instead of east.
Tell me what it is mathematically. Look at the equations. Tell me what the difference is. Look at dr here. Look at dr there. What is the difference? You're right. I'm not saying you're wrong. I'm just saying tell me in mathematical terms. I added the D2 first. Man. Right? DR, D1 plus D2. Here, I added D2 first. That's the difference. But it's still tail to tip. So here I have 3 vectors. So what do I call this? A 4-sided polygon. I added 3 vectors, so I ended up with a 4-sided polygon. And I did tail to tip on this V1. I took the tail of V2, attached it to the tip of V1, right? I took the tip of V2, attached it to the tail of V3. I attached the tail of V1 to the tip of V3. And that's my last one. That forms my polygon. That's when I know I'm finished. All right? So this is just an example of what we just did, right? Tail to tip. Tail to tip. And that's just the triangle I'm normally telling you about, right? This is what I'm telling you. We formed the 3-sided polygon on that triangle, right? Oh. Whoop. There we go. All right. And so, like I said, we're going to be doing a whole different type of mathematics, right? But not anything that doesn't make sense, right? Obviously, if this is vector V, then if I say, let's multiply it times a -1, then what does that do to the vector? Huh? And does what? Flips it. Makes it point in the opposite direction. But we actually don't change the what? Magnitude of the vector. The actual size of the vector remains the same. That's important. But the direction changes. Okay? That's important, right? That's the whole reason, that's what we started with, right? That vectors have magnitude and direction. And one without the other is not enough information. And so we can also scale vectors, right? We can scale them by just multiplying them by a scale factor. So if we wanted to make V, which is here, we wanted to make it a 1.5 itself. 1.5, right, times V, which is V2, right? And that must be 1.5 bigger. 1.5 times bigger, sorry. So V2 is 1.5 times bigger than V. That's what that means. And V3 is what? So what does it mean? It's 2.5 times bigger than V. And what? Huh? It's in the opposite direction. Okay? So, this is what I'm talking about, right? Adding vectors by components. So this is where we get back to trigonometry. Sine, cosine, tangent. Right? So there's no escaping that. We got to remember that. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. SOHCAHTOA. Right? And so, like I said, this is your V vector. This will represent the velocity of an object. The velocity of an object. And that velocity of an object can be, what's the word I'm trying to use? Right now I'm gonna say split. It's gonna be split into components. Components. What is a component? What does it mean to be a component of something? A part. So just that component by itself only makes a part, meaning it's not the whole story. It's only a part. This is the whole story. This is one part. This is the other part. And how they relate is through Pythagoras theorem. Pythagoras theorem, right? And sines and cosines, right? And we see that here. Okay, sine of theta, cosine theta, tangent theta. And we have the Pythagorean theorem here, right? This is the Pythagorean theorem, a squared plus b squared. A squared equals b, c squared equals b, a squared plus b squared, right? Remember that. Okay? That goes to this, right? This is your V vector, right? So, so how do I find my components of different things, right? I mean, of my vector. My components of my vector. My vector is made up of two components. An x component and a y component. How do I find my y component? In this case, it's by sine. Is it that way in every case? No. It depends on what angle we're talking about. Right? And I keep smelling gas right here. So sine, in this case, sine of theta is my y component, right? Because my y component is opposite theta. This is the opposite side to theta. V sub y is the opposite side to the angle theta. What's the adjacent side? Huh? Vx. Vx. What does it mean to be adjacent to? Next to. Right? This side is next to this angle. This side is opposite that angle. So if we were talking about this angle, right? Then what would happen? If we were talking about this angle right here, then the opposite side would be where? Here. And this would be the adjacent side. So it's not always, so don't try to commit that to memory. Commit opposite and adjacent to memory. Don't try to commit, don't say, well, Vy is always sine. That's a lot of people do that. No, it is not. All right? And so, basically, we look at this, right? And we look at every vector is being broken into what? Two components. Look at this vector. V1, this is what? X component of V1. This is the what? Y component of V1. That make those two together make up what? V1. These two together make up what? V2. And so on and so forth. VR, right? The resultant vector, that's what the R stands for, resultant vector, right? It has what? Y and X2. Every vector has a X and Y component. So, So this gives you sort of like a strategy for doing the math. We're gonna get quite a bit of practice at that. So don't worry. You're gonna get plenty of practice at solving these type of problems. That's what this is. All right. And so the reason why we're doing this is because it's leading us to projectile motion, y'all. Right? You shoot a basketball, missile, kick a football, throw a javelin, whatever. Okay? Whatever you do, right? You launch something and you don't launch it straight up or straight across. It's gonna behave like a projectile. Okay? And so you had a little bit of this already in the quiz, right? This is like the tower problem. Right?
Yes.
Because V sub OX is what? 0. When it's coming off if I drop something, then there's no motion, right? Along X or Y, because I dropped it. But what if I rolled the ball off the table? Now we got a different motion. And y'all know that, right? Difference between dropping something and rolling it off a cliff. But if you see here, at every point, we can break its motion into what? Huh? You say what? X and Y, which are called components. We can break it into, at each step, we can break it into its X and Y component because it's a combination of two sets of motion at the same time. All right? And what it's showing here, right, that if I roll something off a desk and I drop something, which one gonna hit the ground first? Huh? They hit at the same time. Why? That is true, gravity, but more specifically, because why? Because their motion or their speed in the Y direction is the same. Whether I rolled it off or I just dropped it. It started off as what? V0 in the Y. The only thing changed was what? V0 in the X, because I rolled it off. But V0 in the Y didn't change. Are you following me now? Okay, good. And so that is what happens right with a projectile, right? And we know that, right? In the military, when we sitting off on the submarine in the sea and we want to launch the missile to hit the poor country, then I shouldn't say that. But when we want to launch the missile to hit the country, hit the terrorist, then we can calculate what initial speed do we need to launch the missile, at what angle do we need to launch the missile so that we can hit the terrorist, based on these equations we're about to work with, right? The same equations. And so here they are, right? And these should look familiar to you, right? This is the what? Golden rule in the Y direction, that's all. See how? Y. Vertical motion. Horizontal motion. Right? So the difference between these two is that what? In the vertical, there is no, what is A? Acceleration for a projectile, unless it's specified to you. You assume in the X direction there is no acceleration. Only in the y. That's why we see the g here. And we don't see a here. But we're gonna get a little chance. Like I said, we're gonna work with that, and we're gonna get an opportunity to practice. All right. So, like always, we go over a problem-solving procedure because that's important in physics, right? That's the meat and potatoes of what we do, right? It's problem solving. Okay? So we got a strategy and we're gonna use it. Alright? So we're gonna create a parabola, right? Well actually no. Well yeah, we'll do that virtually. We're gonna do this one virtually. We're gonna do the free fall lab next week, I think. Or no, next week we got midterm, following week. Alright? So this is just showing you that projectile motion assumes a parabolic type motion. So you can use this equation for all you mathematicians out there, right? But this is sort of similar to a quadratic. All right? And I skipped that relative velocity stuff. And we have the summary. All right? So again, what's important is that we know that a vector has a magnitude and a direction, and we remember all of that, right? Magnitude and direction, right? A quantity with a magnitude but no direction is a scalar, right? Quantity with a magnitude and no direction is a scalar, right? So vector addition can be done either graphically or using components, right? And the sum is called the resultant vector. That was at V sub r. That's when we added V1 and V2 when we got the VR. That's a resultant vector. Okay, and projectile motion is the motion of an object near the Earth's surface. And that's what causes it to move the way it does. Okay? And that's it. We done. Have a good weekend.